go, yeah, will be in this way. This is the contact force. Let me call it F. Okay? So the force is, we call the contact force. And that is the true force that exists in the gears. And again, this is a point of the same at the same position. So here is an action, is a force appear here. So at this side, there should be reaction. So to the contact point here, they have the same magnitude of the contact force, but applying in the opposite direction to this one. And now my question is, I know probably you can ask, why the direction is going in this way, right? So the question is, okay, we recognize at the contact point, they would have a reaction force, and this is the driving. We always starting from the driving side. The question is why the contact force on here is going downward. Do you know why? Because the gear must be also in equilibrium. So this is the driving torque trying to rotate in this way. This force must be in balance of this torque in going in opposite direction. Are we okay?
So it's a reaction?
It's a reaction. Actually, this is a reaction force to this application.
But that's only at a specific point in time.
At a specific point in time, yes. And once this is in rotation, actually the different point on the gears will go to here. And here, again, that is a specific moment of time. Okay? So from driving side, once we figure out the direction of the contact force, and then we simply translate it to here using the action reaction go to here. Okay, and again, this gear must be in balance. So that means here the balance, let me use the different colors here. So this force have a tendency to rotate this gear in this way. So that means the balance must go, sorry. I think this is a driven one. So driven one, that means this will be driven simply by this force. So that means this force multiplied with this RC will induce a driven torque in this way, right?
How are those?
The driven torque, let me call this the TC, will be equal to F multiplied with RC. Would that be your questions? Are we okay? Yes.
I'm just wondering, why is the contact force and the torque going in the same direction?
Oh, this one.
So then they're not in balance.
Yes. Yeah. This is driven initially is no rotation, and for this case, this is go. Okay, so let me change my hand. This is the driving, and this is the driven. So driving go that direction. Okay, so right now for this case this is the driving. So right now it's going this direction. Okay, so initially this is a driven one is there, no motion. This waiting for be driven. So once we have a force spin transmitted, you can see this one basically rotating this way. Okay, and the question is how come this won't be in balance? One step further, I will explain that one. Okay. So now for this one, this is imbalance. That means the T0 will be equal to F times RC, right? For this case. So right now we obtained is this. From these equations, we obtained the force will be equal to T0 divided by RB. So this is RB. Okay, this is T0 imbalance F times RB. So this is RB. And from these equations we have is F will be equal to TC divided by RC. So from here in magnitude, the 2F must be the same. So we come up with the first equations is F will be equal to TC over RC will be equal to TO divided by RB. we build up this relation upon this magnitude contact force. And actually, once we have this relation, the contact force can be kicked away. Okay, so for back to our questions here, and how to transmit it to the torque here. And here you can see this is a driving, so this torque, this gear moving in this direction will drive the gears in this direction. So this is the TC. And what is the magnitude of the TC? Using that equation, TC will be equal to RB, RC times TO. So it depends on the gear ratio. We call the gear ratio. That means the radius of the RC to RB. So for this example, RC, RB, so the gear ratio for this example is greater than 1. So that means the torque has been transmitted, the torque has been scaled up to the gear system. If you could imagine your bicycle, when you come up with the uphill to the campus, you have to switch into larger gears, right? In the way you can sacrifice your speed by saving your torque, your muscles. The same thing, you can use that things to get feeling of this one. Okay, now we have to this information from here to here, and that is a big step, and those information are already here. And so once we have the terms here, then again, to this side, this is this end of the gear of the shaft welded to here. So to this end, that is the action reaction. So here is the torque applied in that way. So to this side here, that is the action reaction. So here is go in this way. Okay, and then that's actually going in that way. Okay, and then in balance, this one must be in balance, so that means going in that direction. So that is go that way. Okay, so now we can begin to do something. And for the first question, once we get that things ready, the first question, the maximum. Again, here in our province, the shaft are the only two elastic objects. So the stress will be happening only in elastic, deformable objects. So the maximum of the stress in a shaft is Tc over J. And C is the outer radius. Again, this is our generic formula. This is C. And here is the maximum if we have a torque like this. Okay. The maximum must be less than or equal to the allowable stress. And this is our generic one. So that means here, for shaft AB, we have is tau maximum less than or equal to 8,000 psi. And torque, what is the torque in shaft AB? T0. And C, radius of the C of the shaft is 0.375, and J is pi over 2, 0.375 to the fourth power. So from here we can see the T0 must be less than or equal to the numbers here I have is 663 pounds per inch. Okay, for this kind of allowable stress or some kind of concept, again, I recommend you to always using the inequality sign, because that will give you much clearer feeling. Yes.
It's pounds per inch.
Pounds inch. The torque, just like it should be pounds times inch.
How do you? Because you have pounds per square inch up there. So how does that?
Yes, and let me do this one quickly. So here the torque times inch, and this one is inch to the fourth, right? Less than this one is 8,000 pounds per inch square. So this cancel, this will be 3. So move this one to here. So basically this multiplies 3 inch. So this one is pounds times inch. Yes.
Is that 8,000?
8,000, 8 KSI. So it's 8,000 PSI. Yeah. Okay. So torque must be force multiplied with distance. That makes
No,
sense.
I didn't understand your inequality.
Yeah.
At first.
Okay. Okay. Okay.
I was a little confused.
The unit.
Yeah. No, you're good now, right?
Okay. So now we go to the shaft CD. Shaft CD, using this formula again, what is the torque in shaft CD? That is TC, right? Shaft TC, we have the torque TC. So what is TC? TC is RC over RB. Let me finish this one. What is RC? RC is equal to 0.5, 0.375. No. RC is the radius of the gears. I forgot to give you the radius of the gears. The radius of the gears. Okay, RCRB is the radius of the gears, so that is 2.45 divided by 0.875, so times TO. Okay, this number basically is equal to 2.8 TO. Okay, so the shaft, the torque in the shaft CD is 2.8 TO. And multiply with C, the radius of the shaft, TC, that is 0.5, and times G, times divided by J, pi over 2.5 to the fourth power, less than or equal to 8,000 PSI. So for this case, that means the T now must be less than or equal to, this number is 561 pounds per inch. So we have two values. One is this, one is this. Which one? The maximum. 561. Okay, so this value equal to 561 pounds inch. Again, using the inequality sign, that will give us much clearer selection of which value to go. Okay. Any questions so far? We can finish this one in a few minutes. So the next one, we want to calculate what is the angle of the twist. So, Labelle, can I erase this part? The angle of the rotation at A, let me use this location DA. And using the relative, the concept, relativity, A relative to B plus B. This one actually represents is the angle of twist in shaft AB. And before we introduced the gear set today, and before this one usually is attached to the wall, so we usually assume this one is 0. But not anymore, because for this case, you can see this one represents is the angle of rotations of gear B. You can see the two gears. One is driving, one is driven. And basically they're logging. So this one is driven logging here. This one is driving. So I try to drive, basically logging. So I try to apply that big of the torque 561. So you can see I drive here, so this one will be corresponding to that kind of the driving, but will rotate a little bit, stop there. Everything will be logging as a static equilibrium. So you can see during this process, the both gears has been rotated by a little bit, right? This gear rotated, that is this part here. And here, from here to here, that is the angle here. Right? I cannot show you, I couldn't disarm mine, but otherwise I will show you. So now how to calculate this one? And for this one, that is easy. That is just like we did before. That is TL over GJ, and that is for shaft AB. We simply plug into all the information, what's happening in the shaft AB. The T is the T. Right now we TO as we're using the TO maximum. Okay, so basically this is this value of 561. So here they use this is 561. And L is the length of the shaft, that is 24 inches. And G is 11.2 times 10 to the 6. And J is pi over 2 times point. Radius is 375 to the 4th power. Okay, so simply using this one here, this one can be calculated as about, these are radian, 0.387 radian. And this one is about 2.22 degrees. Sorry, too low for people sitting in the back, but stand it up. And for gear B, this is the, let me call this is the first information for the gears. That is about the torque transmission between one gear to another one. This is the second information about the gears, which is about the angle of the rotations. So this is the gear C. This is gear B, and this is a contact angle. RB, RC. The gears must be perfectly logging through the gear to the gear piece. And once they rotate, at this moment, this is their contact point on specific pair of the teeth. Once they move on to the next moment, this point on this gear will move to here. This point on this gear will move to here, such that their traveling arc length must be equal. This length must be equal to this length. That makes sense, right? That's a common sense. So we write it out, this equation. For the blue one, the length is equal to, this is called BB. RB times BB equal to, this is called the VC. RC times VC, right? So therefore, so this is the second piece of the information. So using this information for our problem, we can find the VB equal to VC times RC, RB. So that is RC is equal to 2.45, 0.875 VC. So this is 2.8 VC. And why I want to formulate in this, what is this? VC is the angle of the rotation of the gear C. for our specific problems, the gear C is C relative to D plus D. And D is fixed to the wall, so that is 0. So basically, the angle of the rotation for gear C actually is the angle of the twist of the shaft CD, right? Okay? So here the CD is, again, TL over GJ. We plug in the shaft CD, and we plug in the information one by one. What is the torque in CD? 2.80 here. Am I right? Okay, 2.8 times 561, that is the torque. And L, 32 inches. G is 11.2 times 10 to the 6. And J is pi over 2 times 0.5 to the 4th power. And this calculation will be
Was the length 32 or 36 inches?
36, sorry, 36. Okay, I don't have calculation here, I leave it, but I do have the, once we have this one, we plug into here. I do have a calculation for this number that is 0.514 radian. So therefore, we have all the information we can plug in here. So this one is 0.387 radian plus 0.514 radian. So that is equal to 10.48 degrees. So this is radian. So this is our final numbers. Are we okay? So this is a very detailed illustrations of the gears, and Wednesday we go over the formulas, okay, and also the type 2 problems.